Good wishes, class, Physics 103. Today, this lecture, I am numbering it as 1D. And I need to discuss two more maths preliminaries before we dive into electrostatics. So one is something that we're familiar with in one dimension, that is integration by parts, but we'll do it in vector calculus. The other, which is a very necessary in electromagnetic theory, is the Dirac Delta function. Okay, so let me start by asking the question: does integration by parts work in vector calculus? The short answer is yes, if it does, if used with care. Okay, so I'll just illustrate by some examples. Recall that the integration of parts that we know in one-dimensional calculus is based on this rule. That is, if I d by dx is two functions f and g, then this is df by dxg, g df by dx. So if I integrate of this, okay, then of course I get one integral with df by dx gx, the other is fx dg by dx. And this integral is fg, calculated fab, and hence I can write down as, if the integration is f dg by dx dx, then I pick up a minus sign and then transfer the differential to f df by dx gx dx plus the two functions f g evaluated at the boundary. So integration of paths is really based on, okay, this idea that you can transfer the differential to the other function, okay, and you have to pay in terms of a minus sign and uh, and the function evaluated at the border, at the boundary. Okay, so let's take an example in vector calculus. This can be used in vector calculus. Okay. In fact, we'll require this quite frequently, and that is why I'm mentioning it right here. Don't get worried, you don't have to remember, but the fact that this can be done, you must have it in mind. So example, let's say integration by parts by divergence. Okay. Uh, so let's start with a function which is like divergence of a scalar function f and a vector function a. And this, of course, is a product rule. Okay, we know this product rule is product rule 5 in the book. So you will find it in the book cover as well. And this is f, divergence of a, and uh, what a dot, the appropriate differential for a scalar function, that is a dot grad of f. Now I can now do the volume integration of this. Okay, so del dot f dot a. So this is term by term integration of the volume. But we also now know that v divergence of fa d tau of the volume, I can make it a surface integral corresponding to that volume, okay, which is then fa dot dA. Now we know that. Okay, so now if I want to calculate this quantity, okay, so I am bringing it over from here to here, this quantity, okay, then the this is the total quantity over the surface, fa dot dA, and minus of this quantity, a dot. So look at the structure of this integration by parts. I had a differential of divergence of a over a volume integral with f. I will now transfer this differential to f. And the correct differential for to f is grad of f. That's the differential that you can take of a scalar function. So a dot grad of f, you pick up a minus sign, okay, or the integrated over the volume, and you have to pay for by calculating the function f and a, okay, over the boundary. In this case, is the surface. Okay, this can be proved easily. This is a, you can think of this as a proof, but there can be many variations of this. Let me take another example. Okay, so um, how about this? Okay, so f del cross a. So let's work that out. Okay, so this is of course a surface integral. So I'll have a surface integral. Okay, and this will get transferred to the differential will get transferred to del f. All right, the cross a. I'll pick up a minus sign. This is also surface integral. Plus, I have to add the border. What is the border for a surface? The curve C, the path C. Okay, and that would be f a dot dl. Same. Okay, so similarly, many of these product rules can be converted into integrationary paths, and you will use them at different parts of the course. Okay, so this is just to keep in mind that sometimes it's useful to do this. Now let me come to the next preliminary, okay, which is motivating a delta function. I'm not sure you have done it, but in mechanics, for example, let me motivate by saying in mechanics, you have already seen or use an impulse. What's an impulse? Suppose the two balls, two hard spheres, let's say hard spheres collide, okay, and then go away. Let's say they move and collide. And so during that small delta time when the collision, delta time of collision, what is the force? Force is very large, F large. So delta T is small, the time of interaction is small, but F is very, very large. But F del T is finite. This we already know. Okay, but this is in time domain. Then impulse. In fact, in electricity and magnetism, electrical engineers quite often use something as a very sharp pulse. Okay, sharp pulse. This is zero everywhere else. So this is, let's say, a voltage. Okay, at uh, at some t is equal to t naught, there is a spike. It is also called an impulse. You already know this. Okay, so let me give another example, okay, of where this physically it is actually used in physics very, very often. Okay, suppose I say that there is an axis, and at x is equal to 0 there is an electron. Let's say there's an electron at x is equal to x naught. All right, and then I want you to plot the mass, the mass density rho m as a function of x, and there's nowhere else anything is there. So what will happen? This will be, of course, 0. Okay, I'm plotting the density 0, and then what happens when I reach x naught? Suddenly the density shoots up. Okay, and since it is over a negligible space in delta x, this goes to almost like infinity, and then comes down and is again 0. So at x naught, the density goes to infinity, but if I integrate it, of course it's a finite mass, 9.11 10 to the power minus 31 kg. So the integration is finite. Integration is finite, but it's infinity at the point. Now that motivates, okay, by pure mathematicians would not consider this to be a function because it's not integrable, there is no neighborhood and things like that. But it's an extremely useful concept, especially for physicists. So what we will do is we will make it an useful concept by regularizing it and treating it like a function. All right. There is another thing that I can say. Suppose, okay, you have a step function. Okay, let me say a step function. Step function is, let's say it is 0 and then goes to 1. Quite often okay, this is 0 here, let's say, and then it's 1. Let's say voltage. Okay. Something 0 and 1 or X or whatever. Okay. Now I want you to find out what is the differential. Let's say this is not V, this is then time, this is F, and this is X. Now, what is df by dx? All right. So this is 0 and then is 0 here. The slope is 0 here, 0 everywhere else, except at this point, what is the slope? It goes to, with a minuscule epsilon, okay, it goes to infinity. However, so this is by differentiation. But if I integrate, okay, if I integrate, then I get back a finite quantity 1. So if I differentiate, I get this. If I integrate, I get this. So which means the area under this pulse is indeed finite. Okay. So with this motivation, and why do you require it? Because often, okay, we'll talk about a point charge. How do you deal with a point charge, or a extremely thin layer, layer of charge, and so on and so forth. Okay, and that is why this concept is important. So let me go to Dirac delta function and sort of define it for you. Mm, the so Dirac, it's called Dirac delta function. There are all kinds of delta functions. This is called Dirac delta function. So we'll define by the action. Okay, it's not really a function. It's okay. So the mathematicians will not call it a function because of the problems of neighborhood and things like that. But we can always call it a distribution. Okay, that is, it is the main idea of its use is in this integral. Okay, so define a generalized function or a distribution such that, suppose there is an f of x minus infinity to infinity, and this is the function that I'm defining as Dirac delta function. Suppose this is x at, so that goes to infinity at x is equal to x naught, but 0 elsewhere. Okay, then what is its effect of this integral? This integral is finite. That is nothing but the value of this function at x naught. So it picks out, okay, or in other words, suppose there is some function fx, arbitrary function fx, okay, and I have a delta function sitting here going to infinity. That is this x naught, and this is delta x minus x naught. Now, if I integrate, this is 0 everywhere, right? So only thing that it picks out is this point, the value, the f value as a function of x. So if I integrate, okay, so this is 0 because the delta function is 0 everywhere else except at this point, and that value is f of x naught. This is the most central application of a delta function. That is, it goes to infinity at the place of its occurrence, but once it is integrated, okay, then it picks out the value of that function at that particular point. Okay, so what is the definition? this is del, okay, uh, x minus x naught is equal to 0, unless, of course, x is not equal to x naught. Okay, 0 is only at x. If x is equal to x naught, okay, then it is infinity. So in fact, I can write it down as 0, okay, and infinity at x is equal to x naught. All right. But the main idea of this is indeed if I integrate it, delta x minus x naught, then it is just unity, okay, unit function. So delta function, in other words, delta function is a function that vanishes everywhere. Just I'm speaking, saying it, same thing in words, at a single point, but nonetheless has unit area. Okay. So we have already seen delta as a different, the function that I showed you, okay, uh, is sometimes called the Heaviside theta function, that is step function. All right. So at A, there is 1, otherwise it's 0. So that is this function. It's called theta function, capital theta function, theta x minus A. Okay. So you have seen already that if you differentiate this, what you will get is uh, what you will get is the infinity. Okay, so function, so this is the delta function at x is equal to A. All right, so that is the thing that I have already illustrated is one way to be. There are many ways of viewing this function because it has uses in different contexts. Okay, let me it is also can be considered, okay, to satisfy the mathematicians as a sequence, okay, a limit of sequence of some regular function. Okay, so but what is the nature of the regular function? Which will grow progressively narrower as a parameter is varied. Okay, so it's a peaked function. Okay, so anything that which is which can be sort of peak. Okay, and then this width, if I make it narrow, keeping the area under this curve finite or 1, okay, then it becomes the sequence. Let me illustrate that. For example, delta x can be considered, okay, to be a sequence, okay, of alpha, let's say del alpha x, with alpha going to um, tending to infinity, okay, sine alpha x by x. Alpha, I'm sure you know sine alpha x by x. Okay, this 1 by pi is such that it can make it, the integral can make it 1. All right, so this is a sequence. You plot sine alpha x by x. I'm sure you already have done this in maths courses. It's very important in physics also in various. So this is, mm, sorry. Okay, so this is like this. This goes like that. Sorry. Okay, you try and plotting that. All right. So we can also write down sine alpha x by x. Okay, as half of minus alpha to plus alpha eikx dk. Okay, satisfy yourself. Okay, this is simple, and hence there is a another way of defining, which actually used in quantum mechanics and many other electrical engineering a lot. There is del of x, delta x is nothing but 1 by 2 pi, is a normalization factor, minus infinity to infinity eikx dk. That's also a delta function. Okay, and you will see this in maths in Fourier transform, uh, again your later maths courses. It can be considered as a Gaussian representation. What is Gaussian? It's like a normal curve that you must have seen, right? So you can e to the power minus x square, okay, is suppose is like such a function like that, right? This is Remember there's a minus here. Okay, this sigma controls the width, controls the width of this. Okay, and so now if I make sigma going to 0, the sequence, so let's select next sequence I do is I increase sigma, the area remaining the same, it becomes like that. And then I still make the sigma narrower, it goes like that. All right. So let's say this is sigma 1, this is sigma 2, this is sigma 3. So I am making sigma less and less 0. The area under the curve will actually become 1. This is the normalization factor here. Okay. So you can think of a narrowing of the Gaussian. This is another representation of delta function. There is a Lorentzian. Okay. The Lorentzian shape also is the Lorentzian shape is also a little different, okay, but most optics is like that. In resonance, you must have seen. In mechanics, the resonance curve is a Lorentzian. All right. So now there also it is controlled by the epsilon. So now you make the epsilon small, the Lorentzian shoots up almost to infinity and then comes down. So that can be also a sequence in Lorentzian representation. So finally, if epsilon goes to almost 0, as epsilon tends to 0, it becomes a delta function as a function x. Okay. So there are many different ways of representing it, but most important to us in this course is the some very useful properties. One of the useful properties which you can show, I'll give it in the tutorial, okay, that if this is a constant a, which could be positive or negative, okay. If it is positive, then of course 1 by a del of x. If it is negative, then 1 by a del of x. Okay, it's a very useful property. Please prove it. I think it's already solved in the book as an example. But as an important corollary, uh, delta function is an even function. K is equal to, let's say, -1 or 1, it's the same. Okay, so just that the Dirac delta function is in fact a uh, even function. Now let's generalize this to 3 dimensions. This I've shown in 1 dimension, but to us in electromagnetic theory, since we are dealing with vector calculus, we need to do it to 3 dimensions. Okay, so in 3 dimensions, let's say all space. So we write down as del 3 dimension x, y, z. So there is a delta function at some point x naught, y naught, z naught. Okay, or for example, in this case, it is just sitting at 0. If there is a delta function sitting at 0, which is x minus 0, y minus 0, z minus 0, dx, dy, dz, integrated over all space, that should give you 1. That's the definition. Okay, and of course at 0, 0, 0, this function is going to infinity, but integrated over the origin, it is 1. Okay, so similarly, suppose I do f of r. Now it's a not a single variable, a single dimension variable, but a 3 dimensional variable, f of r del q r minus r naught. Then it picks out the value of the function only at r naught, the fixed point, so f of r naught. Straightforward generalization of the delta function definition that I have done right away. Okay, let's do some quick examples. Okay, uh, let's see what is one of the relevant things that we need to do is to what is this divergence? Okay, and we know the importance of such functions, right? In electricity and magnetism, in gravitational, all our force functions are 1 by r square. We're not dealing with force at the moment. And how does this function actually look like in geometrically? This is, let's say, this is 0. Okay, then I have it's very large because r is small initially, and then let's say you must have plotted this many times. So, and then, but as we go away, okay, then it becomes smaller, 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 and so one by, it becomes one by square, right? So I had given you this example in the lecture on divergence itself. Okay. So now, what is the divergence everywhere? The question is, what is the divergence everywhere? Okay. But this is spherically symmetric, and hence we can use the divergence formula. So this must be equal to, let's say, try and calculate to using that. So this is only the first term. There's 1 by r square, 1 by r square, del by del r square, 1 by r square. There's only the r term. Okay, so that gets cancels. So this is equal to 0. So does it mean that divergence of this quantity is 0 everywhere? But on the other hand, let's look at, but if there is divergence is 0 everywhere, where is the source? The source is sitting at here. Is the divergence 0 at x is equal to 0? And what happens at x is equal to, at r is equal to 0? At r is equal to 0, this is going to blow up. So can I actually do this operation? This operation is really not, this operation is really not valid when r is equal to 0. There is a singularity sitting there. Okay. But I can always convert this. Uh, let's say I take the divergence over all space. Okay. Then I can convert this through the fundamental theorem. This is a volume integral into a surface integral. Divergence theorem goes to r by square dA. Okay, for a spherical symmetric. So now I take my spherical symmetric, let's say any r, a sphere of radius r, then this becomes 1 by r square, r hat, and dA is capital R square sine theta d theta d phi r hat. So r hat is of course 1, and 0 to 2 pi, 0 to 2 pi will give you, okay, so that sine theta will give you 1, and this will become 4 pi. Okay, so if if this were indeed true, that it was equal to 0, okay, then this all space should have been 0. But if I include the origin and include or integrate over the sphere S, then it is 4 pi. So which means this is exactly what a delta function is supposed to do. At the origin, there is a delta function, because that is the source is there only at the origin and nowhere else. And hence divergence is 0 everywhere except for r is equal to 0. And what is there at r is equal to 0? Okay, which can give you 4 pi, must be such that the, okay, so if divergence is 4 pi del q r, which means it is 0 everywhere, 0 everywhere except at r is equal to 0. Okay, and what is the height at r is equal to 0? It's 4 pi. So 4 pi, okay, because if I integrate this, including the 0, then I get a 4 pi. This is important result. Okay, we'll use this extensively in the next lecture. Okay, so more generally, this I've used r hat r, but as I had said you earlier, okay, this is also true for, let's say, this is xyz, this was r is equal to 0, but suppose my source is at r dash, this, okay, then this is r dash, okay, so any other point, at any other point from here is this curly r. So this is also true of this curly r. Okay, that is this my source is here. I just, instead of at origin, I have it put at some point which is r prime. All right. So we already know that grad of 1 by r is minus r hat by r square, and divergence of minus of r by r square, okay, would be divergence of grad of 1 by r. Okay, so this is nothing but the Laplacian del square of 1 by r. So what is del square by 1 by r? Is minus 4 pi. This is an important relationship for us. That is, the Laplacian of del square 1 by r, okay, is, this is 1 by r meaning for the source coordinates, wherever the source is. Okay, so then this indeed is an important relationship. In fact, all these relationships are important. Okay, so del square 1 by r is then minus 4 q by del q r. Okay, so let me put this as, you can see immediate relevance, that potential due to a point charge we know is, why am I doing all this? Because in the next chapter I'm going to show you, we already know that the potential is q minus 4 pi epsilon naught r, but del square v, if this is v, is minus q epsilon naught del q r. Okay, if I that's exactly the point. Okay, but we'll discuss this in more detail soon. Let's take, all this will make sense if I can take some example. Uh, Let me take some example to show. What example I'm taking? Let's see. Um, Simple. Let us take example. Let's say 1D2. I've given something earlier. So let's calculate this for all space. For all space, let's say e to the power minus r, exponentially decaying, then divergence of r hat by r square d tau. All right. So this, by what we have just done, okay. So let's say I'll call it method 1. That's okay. How simple it becomes, you can see now. Okay. What did we say? Divergence by r square is nothing but, if you remember, uh, divergence of r by r square is 4 pi del cube r. So let me just plug that in. So this is all space. So this is all space, and e to the power minus r, this is 4 pi del cube r d tau. Okay, so what will that be? So it will be, we know that this is the function, this is r at equal to 0, so e to the power minus 0, that is just simply 1, 4 pi, and that is nothing but 4 pi. In method 2, you can try, I will not do it here, but what I have illustrated, you can do without using the delta function. Now you can see there is a function f, and there is another function g, which is divergence, and hence, okay, try using integration by parts to get the same result. Okay, but this is, you can see the kind of convenience if you use my delta function. All right, so it becomes very, very easy quite often, but in this course, mostly you will use this idea to look at singularities as r goes to 0 or in any one dimension collapses into a singularity. Thank you. Uh, I think what I would like to say is that, with this, I come to the end of the sort of mathematical preliminaries. Okay. Um, so these are brief preliminaries, and we are now all set to dive deeper into electromagnetics. Okay. And as an advice, I would say you need a mastery at the level of the language of vector calculus, okay, to fully appreciate the beauty, one of the central paradigms of our current understanding of the world, that is electrodynamics. So this first week, it's worth investing a lot of time and energy at picking up the language. Okay, you might think, why am I doing this? Is this a physics course? But yes, the beauty of physics will only come out, okay, if you master this language at this level, okay, not at any deeper level. You will do all these also in maths in some other course, as mathematicians do, okay. But to be able to appreciate the physics at the level at which I have done here is good enough for the course. Okay, thank you. All the best.